All right, should we go ahead and get started then?
Yes.
Yes, please.
Yeah.
Okay, so I'm very happy to introduce Varun Mapara. He has done his bachelor's in India from Maharaja Sayajirao University of Baroda. And in the same university, he has done his master's, the same as where I did my master's back in India. And in those days, our specialization was nuclear astrophysics. And currently he's pursuing his PhD in University of South Florida, almost in his last year of his PhD, and is working on transition metal dichalcogenides. And so he's going to talk about some interesting facts about this thing through this paper today with us. So what to you, Varun?
Okay. Thank you, Khushi. Thank you very much for the introduction. And thank you, Western Michigan Physics Department, for inviting me for this interesting talk. So this paper is basically work done by Christopher Stevens, Jagannath Paul, and Timothy Cox at the National High Magnetic Field Laboratory, while Prasanna and Umberto Guterres provided CVD grown sample in this work, while Dmitry Smirnov and Dr. Steve McGill provided their support at National High Magnetic Field Lab Tallahassee, where this experiment is performed at 25 Tesla. And our collaborators, theoretical collaborators, are Dr. Koch, Dr. Perakis, and Dr. Vladimir Turkovsky. In this particular paper, Dr. Turkovsky provided 2D FT calculation for theoretical matching of the data and provided insight about Biexciton dynamics, as well as provided this nice behavior of these TMDs that called non-Markovian memory effect. I'm going to talk about this in next slides. We have a collaborator at University of Alabama, Birmingham, Dr. David Hilton. He do terahertz spectroscopy, and we often share ideas and our collaborations with them. So let's get started. As a user at National High Magnetic Field Lab, we have opportunity to do experiments on two different setups over there. The first setup is cell 1 setup, where we have a 10 Tesla Oxford Instrument magnet, where we generally perform our smaller sample because we can go very near to the magnet as fields are moderate, but still it's a high field measurement. And this is the work done at 25 Tesla. This is the setup. As you can see, there's a 25 Tesla magnet, and this is the monster equipment. I'm going to talk about this monster equipment more and almost thoroughly, because that's where the whole nonlinear spectroscopy and optical stuff that we do, we can do it with this monster setup. So while this work was happening at Tallahassee, I was in my third year of graduate school, and my task is to set up 7.5 Tesla magnet here at USF. So this is my lab here at USF. We have 7.5 Tesla magnet. This is our superconducting cooling mechanism to cool down our sample, while magnet is a warm bore, so we can actually insert the cryostat inside, and we can study really small samples, like few micron samples with very high spatial resolution at the beam size. Our beam is like 20 micron maximum size, where as I will explain, this is like 4 beam we are shining on the sample, and we have to really worried about the beam size, that it has to be smaller than our sample size. But nowadays, these TMDs, transition metal dichalcogenides, are available in very large forms, almost a millimeter size. So we have a little freedom in our spot size. But that was my work, and I'm still continuing on this TMD's work. So let's go to the paper. I break down this paper at 4 different parts. The first one, we're going to refresh our knowledge about transition metal dichalcogenide, why they are so interesting to study, and why we need this coherent nonlinear spectroscopy, and the way we are doing experiment, why they are different from other experiment, and what they can provide, which other experiments are lacking. I'm going to talk about those parts. Then I'm going to talk about specifically the results and the technique used at 25 Tesla setup over there at Tallahassee when the experiments are done on MOSE2. And then we go for the results and the discussion, and we try to learn what type of physics it gives us. So let's go to understand transition metal dichalcogenide. So this uh, MOX2 type transition metal dichalcogenides are almost 60 different elements, starting from we have like 60 different combinations of it, where M is a transition metal, while X is a chalcogens, where chalcogens are sulfur, selenium, and tellurium. And there's a very big class of transition metals that we can combining, and most famous examples are tungsten diselenide, molybdenum diselenide, tungsten disulfide, and molybdenum disulfide. They are like heavily studied materials in the past decades. After we understand that this material can be actually exfoliated with the Scotch tape method, and can be done, can be produced via chemical vapor deposition. These two very famous technique to produce the samples of this method. As we know that in 2010, Andrei Geim and Novoshelov got a Nobel Prize for making graphene out of a Scotch tape method. Like just one layer of graphene can be extracted from the bulk material via just Scotch tape method, just using a regular Scotch tape that we have it on day-to-day office supplies. Why it can be done with the Scotch tape is because where in plane bonding is very strong, while out of plane bonding is just bond by van der Waals interaction, and it can be easily peel off, and you can go all the way to one layer. In the beginning of this last decades, people started with the Scotch tape method, and then they come up with a more nicer quality sample with the chemical vapor deposition. And then after now this combining both together inside the chamber, it's called ALD measurement, ALD type of technique, that we can have a very nice big millimeter size sample, and we can study them thoroughly. In this particular talk, the samples are provided by Prasanna's group in their make with this chemical vapor deposition system, and it's a nice coverage on a substrate. So two properties that I like to explain here thoroughly is this: why transition metals are very famous among the device application scientists, that this can be very useful in making lasers, sensors, because when you go from bulk to monolayer, as you can see, band gap here, from bulk to monolayer, we have a indirect to direct gap transformation. What it does is indirect band gap transitions are hard for the electron to happen. It requires more energy, while monolayer, the band gap also increases, and this band gap falls right into the optical spectrum, optical side of the electromagnetic spectrum, where you can actually study with lasers and white light even to their optical properties. And this is providing us very nice platform to understand physical phenomena, as well as this can be used as a device application, as graphene lacks the band gap like what we have. So this becomes not semiconducting material to semiconducting direct band gap semiconducting material. For both MOSE2, WSE2 have this this transformation. And generally, the structure of a TMDs is metal element in a middle and sandwiched by two layer of atom of chalcogen. So it's basically not one single atomic layer rather than three atoms, but just one layer of materials. And it's very, we can study it with optical transformations and other optical phenomena. So the consequence of going from indirect to direct band gap is you see this is a PL spectra of TMDs. The first, the green line is a 3-layer, 2-layer, and 1-layer. When you go from 3-layer to 1-layer, the PL increases drastically, and that says us that in a monolayer, these materials have a very strong light matter interaction, and we can study them. Yes, can you hear me?
Yeah, we can hear you. What is PL? Sorry.
Photoluminescence. So generally, you excite these bands with the green laser. It's a higher energy laser, 515 nanometer laser, and so electrons are basically go from the conduction band to valence band, and when they come back to the conduction band, you see this type of spectrum, and it's called PL spectra. This technique is used to characterize the sample and the sample quality. So this is the main signature when you're actually exfoliating the sample and making your sample. When you go from 3-layer to 1-layer, your PL increases very drastically, and that is like significant that yes, you have achieved that you have only 1 layer of sample now. And this very strong light matter interaction is the first signature, and that actually motivates spectroscopists and device people that yes, this material can be used as in devices because it's a very nice sharp PL. Second property that I like to discuss here is the spin orbit and valley properties. So this material lacked the spatial inversion symmetry. As you can see, this is the unit cell of 2 layers TMD, where metal atom is right on top of a chalcogen atom. But when you remove this, we have only left with just 1 layer, where if you flip it 180 degree, it no longer the symmetric condition, and due to this spatial inversion symmetry breaking, it gives rise to 2 type of phenomenon. The first one is a spin orbit coupling, and the second one is spin indexing. So when we have a symmetry breaking, we have electromagnetic gradient in plane, which couples with crystal momentum, and we have a spin orbit splitting. It's almost, you can assume that as in this material, the spin orbit coupling is very natural because of a heavy atom right in the middle, and that's dominating in that band structure, while this spatial inversion symmetry breaking gives us at these corner points, as I showed you in the first slide, that we have a valleys at the K points, and these valleys are actually reciprocal to each other, as you can see here. So this is a K point valley, and this is a K prime point valley, where the spin is just different. It's the same energy, everything's same, but the different energies. So now how this reciprocity or reciprocal behavior in the valleys, we use it or we exploit it to study this valley mechanism. And if you know the term of valleytronics, it's a new term that people are understanding it now just because of this TMD, that it has this type of valley structure, and this can be excited with some type of light. It's called a right-handed circular light or sigma plus type of light. So when you apply just sigma plus type of light, it just excites the K valleys, and sigma minus light just excite the K prime valleys. So you can selectively excite just one side of the beryllium points, like just one beryllium set of points, while the other type of light excite just the reciprocal side of the beryllium zone. And this is called valley polarization. So different type of polarized light can excite only one type of valley. And this mechanism, or this nice behavior, that's what we are using it. So we learned two nice properties. The first one is being, it has a very nice strong PL, so light matter interaction is very, very dominant here. And the second one is the valley polarization, that these two properties, we're going to use it in our research. So now let's go to understand how the exciton formation and Biexciton formation happen in MOSE2. So as you can see here, the lowest band and the highest band, the band minima in a valence band is have a same spin. So this is spin allowed state, right? While in WSE2, that the research that I am doing it right now, they have a spin forbidden state, and those electrons cannot go over there, and they are called forbidden state, or excitons created over there are called darker exciton. While in MOSE2, we have a freedom that these excitons are optically detected, and these excitons are called brighter excitons. Now, it has this, and of one more thing that I like to say, that these excitons behaves almost in our favor when you actually cool down the sample. When we in this paper, we study the sample under 10 Kelvin, while generally 10 Kelvin, because of that's the limit of what we can achieve at the 25 Tesla setup over there. While we have in our lab, we can go all the way to 4 Kelvin liquid helium temperatures. So there is no thermal drift, as well as excitons can create and they can bind, and the lifetime measurement, what we try to see here and what we try to study here is in our favor. It is more like a uniform. It provides a nice platform to understand this exciton dynamics. So as these mechanisms are bound by very strong interaction between the valleys, and these valleys are combined to each other, and it's called intra-valley transitions. Like these electrons can combine with these holes, and this electron can combine with these holes. It's still not the combination, but we can say that it's a quasi-particle or a 4-point correlation. If you read the paper, they said more about this 4-point correlation, and why 4-point correlation is very important to see the changes in the results that we're going to discuss later. So I'm switching from the properties of GMDs to the technique that what we are using here. So we are using non-linear spectroscopy. And when light interacts with dielectric medium, there is a macroscopic polarization induced inside the sample, which can be understood by this equation, epsilon 0 chi E. And if we do the series expansion, we have this first 3 term here. The first term is the term that gives rise to PL, your photoluminescence. The second term is in a centrosymmetric system, this even though it has a spatial inversion symmetry breaking, but still, if you see the system from the center, it's the same type of atom arrangement, and that's why the second term goes to 0, while the third term is the first non-linear response. Let's understand this linear response and non-linear response in a very basic way, that if you increase the laser power, you will see the photoluminescence signal increases, while this nonlinear response requires 3 laser pulses to create that macroscopic polarization in the system, and that's why they are different from each other. And the second point is that PL cannot give you more information. It's just a one Gaussian like peak feature. You can understand the broadening, and you can think of there is a many-body interaction going on in the system in these bound states, but it cannot. It's not a direct signature that you can understand. That it's from biexcitons, it's from trions. It can be exciton-exciton correlation. So that's why we have, while this nonlinear spectroscopy, we can study the coherent lifetime here. So meaning that we are almost see the system in at different times, and we can see that yes, there's a exciton creation, and at this point there is a biexciton creation, and the now exciton screening is happening. So that's why this technique can gives us more insight what is actually going on in this biexcitons and trions creation in this TMDs. So I'm going to talk about how we use 3 laser pulses to induce the polarization in a sample. So here we have 3 laser pulses separated by particular amount of time, and let's understand what each laser pulse is do to the sample. So first laser pulse arrives and create a population um, into the sample between the ground state and excited state. The second pulse arrives and convert that population into polarization. And the amplitude of the population is determined by the relative phase of electric field of B, and the polarization induced in the sample varies sinusoidally with a spatial period of KB minus KA. So KB and KA are the wave vectors associated with each laser pulses. And when they are constructively matched to each other, we have maximum intensity of 4-wave mixing signal. When they destructively interfere, so we have a lesser intensity. So how we determine the constructive interference and the destructive interference? So we make sure the timing between this pulse, if you know the Michelson interferometer, when the two laser pulses arrive at the same time, we have an interference pattern appearing, and that interference pattern tells us that there is no timing between the pulses. And as soon as you start delay in the first pulse timing, you have a pattern changes, and you can actually see the interference pattern goes away. So this is how we design our experiment. While it's designed so that the vector addition of these 3 pulses, now A and B gives us a signal, while the third pulse arrives and breaks the grating that is created by A and B pulses and shoot it to the direction of the missing corner of this box. As you can see, this is like a really clever experiment where you have a 2 syringe, and with the same amplitude, if you shoot it, you have a third vector addition happens, and the third dimension, that's where the purple liquid is flowing. We have almost the same way, but the 3 laser pulses, vector addition happens, and we choose it with the phase matching conditions that our signal appears at the missing corner of the box. And we study this missing corner of the box with the slow single channel detector. And these 4 pulses are given by this monster apparatus. Monster is like multi-dimensional optical nonlinear spectrometer, where you have a 4 Michelson interferometer right on top of each other, and here you can tell them when the pulses are at time 0. You can see a interference pattern between A, B, BC, and C and a reference, and we make sure that the pulses are at time 0 before we start experiment. So before I go to actual paper and the data, if you guys have any question at this point, you can bring the question right now, or we can do it at a later.
Varun, we are almost out of time, so you should kind of hurry up.
Okay. So as these 3 pulses we have, we shine it to our to sample, and at Tallahassee we have in-plane magnetic field, so we have to go through this periscope measurement, and let's understood this part a little bit correctly, and then we can go straight to the data. That we vary the timing of pulse A, while the B and C stays the same. So you create a coherence with the pulse A, and we map the coherence created by pulse A. So we can go straight to the data here. As you can see, there's a increase in both negative delay timing and the positive delay timing when the in-plane magnetic when the magnetic field is applied. So it's a negative delay can be understood here that pulse A is trails behind of B and C, So people don't understand this behavior, and they say that it's a causality changes, but this is basically where the 4 particle comes into the picture, where 2 bound electrons create quadrupole moment. So only one pulse cannot de-excite them. So you need a second pulse to de-excite them, meaning that we have 2 pulses. It's basically 4 particle correlation, and to de-excite both particles, we need a second pulse to do. So this is where the 4 particle comes into the picture, and here, that's where the Biexcitons plays the role. So I will, because of time, I will go right to this picture here. So as we increase the field, what we see here is the difference between the states are more and more increased, and due to the screening of the excitons, there's a longer dephasing time. This coherence created by pulse A is getting longer and longer. So as you can understand that if we increase the field, we have a more coherence, and we can actually tune this coherence. That's why the paper title with the tuning of the Biexcitons created in this material. This is the data that we can see here, and we study co-circular polarization and cross-circular, where co-circular just excite one valley, while the cross-circular excite both valleys and create Biexciton, and that's why cross-circular you see a more dephasing lifetime. I think I can stop here, and we can discuss if you have questions.
Perfect. Thank you very much, Varun.
Mm-hmm.
And now if you have questions.
Yes, thank you, Varun, for that. And apologies, it's a short time to present high-level information. I have a question. It's
Yes.
maybe more basic. Can we go back to the slides where you were showing the symmetry breaking?
Yes. Yeah.
Okay. Yeah. Okay. Yeah. So there I see the monolayer.
Yes.
And according to my understanding, you are saying that what you do is you shine a laser into that monolayer. And what
Yes.
happens, you create these Biexcitons.
Yes.
What you're doing is you are cleverly shining the laser to excite different parts of that
Yes.
crystal, which is maybe you can shine the K and have that valley index. So you
Yes.
talked about that eventually when you are now trying to analyze this, you look at it as a many-body interaction.
Yes.
And so is the interaction between the different Biexcitons excited at each different lattice point? And if that's so, how is it? Because you said also these are like bound. And so if they are
Yes.
bound, how do they interact? Is it like a nearest neighbor interaction?
Yes.
Can you
Yes.
explain more on that?
So think of it as this picture first. So exciton created here and exciton created here in the actual lattice. They think about it. This is just a one layer of material. So you can think of it as a tiny village where a change in one valley can almost change the whole system. It's not just the one valley that is getting excited. It's almost all valleys are getting excited and kind of talk to each other because they are so near to each other. This is almost I would say this is a couple of angstrom. I think 2 or 3 angstrom difference, and because screening the Coulomb because it's just a one layer, Coulomb interaction is very high, and that's why we call it a stout exciton. This is like very tightly bound excitons, and when you have a like electromagnetic gradient in the system, meaning all electrons almost getting coupled with each other. So as I think I try to make one figure to understand this better. Yes, this figure here. That as you can see, I mean, they are bound by their own holes, as well as they acquire the quadrupole moment. So you can say that there are two dipoles side by side, and they acquire a quadrupole moment. So when one dipole moves, the other also try to react and moves with each other.
I mean, this is very interesting. What's the mechanism that holds this together? I mean, is it like what the phenomena in PCS where you have the Cooper pairs, or what ensures
This is
that
all. So this is all, believe it or not, this is all because of this symmetry breaking. So you can think of it as an, if electron goes in this direction, it sees different type of Coulomb interaction where the electron going in this direction. Think of it like that. Let's see this chalcogen atom is very, it's in a little bit sidewards, right? It's not exactly in the center, like what we see is in a nice cubic system. So this one thing is that very high Coulomb interaction, and other thing is that there are gradient in the system that governs this mechanism. First, people this type of behavior in gallium arsenide, um, where this data is acquired in 1998, the exact same measurement that we did. And you see this in gallium arsenide, you have one more state in between this ground state and excited state. So you have a like flipping, like tuning and detuning between the state, and you can see there is a sinusoidal wave pattern. I mean, almost a formation where they don't understand this behavior, and this is what we call it a non-Markovian memory effect, where you need two laser pulses to de-excite, while this is just because of the in-between tuning of the states. And
okay. Maybe let me allow others to ask so that we don't turn this into a conversation. Yeah, I had other questions on the paper, just a little bit of definitions. When they
yes,
talk about the four-wave mixing, is
yes,
it, and I was, what does that mean? Is it because I saw you are using only 3 pulses, so that's
yes.
not what you
So
mean by four-wave mixing.
so so we call this four-way mixing because it's these three pulses and the signal. So think of it as in this, you see there's a three pulses wave vectors and the signal wave vector. So it's a 3-pulse 4-wave mixing, meaning you can acquire different combinations by changing the sign of these 3 pulses and the changing a sign of of signal where signal appears. Signal can appear also here if you change the sign of minus K, minus KB, and plus KC. So that's why it's a little, the guys who come up with this idea first, they are, this technique is mostly used for 2D measurements, so two-dimensional Fourier transform, while we take this signal into slow detector and a chopper, while if you study this in a spectrometer in the same technique, you can acquire a 2D map where you can see the line with broadening and stuff. So that's why it's called 4-way mixing, because of combination of signal plus the 3 beams.
Yeah, it's I feel like it's bad naming, but anyways, they discovered it. They get to choose what they.
Yes. You can see that
Well,
they.
let me allow for other.
If we have any other questions, I can take one more person's question, but then it will be time for us to move towards the quiz.
I have a question.
Yes.
Yes.
You were talking about the quadra-magnetic moment things that were being created. How
Yes.
long do they last before they uncouple?
That's data right there. Almost
okay.
a quarter of picosecond. So
Okay, cool.
you can,
Thank you.
so there is a, I mean, there is two things I want to just one more point here is that coherent lifetime is different than a lifetime of a quadruple moment. So what we understood is a coherent lifetime here. So you make a coherence and you break the coherence. So they are in a coherent state for almost a quarter of a picosecond, while their actual lifetime is hundreds of femtosecond. But as this is like a process, the whole creating coherence and breaking it, you can see it all the way to quarter of picosecond, while in cross you have almost half a picosecond. Yes.
Okay.
Okay, thank you.
Perfect. So now I'm going to post a link in the chat, and I would want everyone to access the link. There are 5 multiple choice questions, and you will have, let's say, 5 to 8 minutes for answering it. And if you have any other concerns in while accessing the poll, then just let me know. The link is posted in the chat.
Hmm. Khushi, are we gonna have time to ask follow-up questions on the quiz? I feel like there was a question that was not that was not, but we can talk about it afterwards.
Yeah, I was just going to. Anyways, yeah, it's okay. We'll let people continue writing the answers. If you want to submit an answer as well, please do, because otherwise we
I've
won't
already
be able to.
submitted mine.
Oh, you did? Perfect.
Yeah, yeah,
Oh, yeah, I did got.
yeah. We get 0. But yeah, Varun, this is very interesting stuff. Thank you for taking your time and doing this. It's one of the reasons we started General Club to learn more about different kinds of physics.
Yes, we because of pandemic, we cannot go to Tallahassee to perform on my samples. Otherwise, I could have presented my work other than Chris's work. But at 7.5 Tesla, think about it, that we run this experiment at 25 Tesla. Earth's magnetic field is 0.00005 Tesla. So 4 zeros and 5, that's Earth's magnetic field. It can still flip the needle, right? While this is 25 Tesla, and I have downstairs a 7.5 Tesla magnet, and it looked like it's still, the field is not enough to split those electrons far apart and study. So we'll probably
Yeah,
will have a time soon at National Mag Lab, and we will perform experiments. Yes.
yeah. That's very interesting. Actually, I'm a theory guy, and I had another question which we will talk about once the formalities are over.
Yes.
My interest is in quantum computation, and so one of the thing I saw in the paper is that you can use this Biexcitons to build qubits, and I was like, how? So I'm interested to know those things, and yeah. So
So
being a theoretical physicist.
one thing for all the audience that I want to point out, this it's very related to the paper and your question also, that because it's a 4-particle system, think of it as in 2 qubits combining to each other. So one qubit cannot move by itself. If so, you have to move the 2 qubits by 2 laser pulses. So that's why they think that if we can create so coherence is basically what you require to make any system work as an qubit, or store some information, that you shine a light and it will store some information for you, and you shine a different type of light, you can extract the information out of it. That's something I understand from a magneto-optic Kerr effect. That's what we do it in our lab too. Your CDs and your DVDs are work on that magneto-optic Kerr effect. But that's why this Biexcitons are 4-particle system, and that's why people interested that can we make a qubit out of it. That's the whole, I think, whole scenario. And I think if you go into that direction, you'll stumble upon papers that they actually use it in impurity-based crystals. Yes.
Okay, so keeping an eye on time, I would say I think we have submissions of answers. So for now, I'll just say we will have time for grad student opportunities, which will be presented by Abby Flowers. So over to you, Abby.
I'll take the presenter.
Varun, would you like to stop sharing your screen so that somebody else can?
Sure.
All right. I got it, actually, I think. Okay. So this week for grad opportunities, can you guys see? Is it too small?
It's too small. Yeah, can you just make it
Okay.
please?
I'll make it bigger. So this week for grad opportunity, or this month, I put the graduate college grants on there with the link so people can start thinking about applying for them for the fall or next year, but I believe all the deadlines for the spring have passed for ones that would be relevant to us. The American Association of Physics Teachers Conference is from July 31st to August 4th this year, so as a science ed student, I will probably be going to that, and it will hopefully be in person in Washington, but we'll see. But yeah, that's July 31st to August 4th. And then the Physics Education Research Conference, which piggybacks off that, is August 4th through 5th. There's the 6th International Conference for Young Quantum Information Scientists from April 12th to 16th this year. And then I left the postdoc positions from last month on there. And then, I put the qualifier exam prep resources that you sent me, Mankoba. So just some stuff to prep for the qualifying exam. And then just thank you for coming. I put please take our quiz. And thank you so much for presenting, Varun. That was a great talk. So that's pretty much it for grad opportunities.
Perfect. Thank you very much, Abby. So what next, Ming? What do you want to take over from here?
Are you not going to reveal to us the winner?
So
I think 2 people are eligible to participate. It's only Josiah and Dave.
and let me check.
So actually, there's a book award for the highest score, and
Actually, Dave has not submitted the response. So
Josiah gets it by default.
yeah, I was going to ask you how do you want to go by that, because there is nobody.
Oh, actually, yeah, no, Josiah is not a member of the physics department, so you are not
But
eligible.
we did not say that they should be member of a physics department. We said it should be universities, faculty, university students, no?
Yeah, they have to be a Western student, otherwise the.
Oh, Josiah is
Yeah,
not a
that's fine.
Western student?
Is he? Are you
Josiah,
at
are you?
Western, Josiah? Actually, that's good. Josiah, respond to us. Are you at Western?
Yes, I am a student at Western, but I'm an undergraduate student. So I've been getting
Then
this
that's
email,
fine.
and I finally decided to show up for a meeting. I didn't know if this is supposed to be for graduate students only or something.
No,
No,
it is for
no.
everybody.
I actually thought you from University of South Florida.
No.
I didn't know you.
I'm
Western.
taking
Sorry,
the analytical mechanics from Pansilla, Intro to Modern Physics from Bautista this semester. So I'm getting
you
through
are
stuff.
perfect. Yes. So by virtue of you being the only one eligible to get the prize, if you submitted your quiz, what was the score, Khushi?
Okay, let me check and I'll tell you his score.
Probably not very high.
It's. Do you really want me to tell you the score?
Okay, well, let's skip it. You are, congratulations, Josiah, you are the winner. Please send us your email and then I'll get you the book, your book. You win a book for participating.
Oh, cool. Can I just put it in the chat?
Yeah, please give me your email in the chat.
Oh, should it be the Western email or my email?
Anything should
Whichever
work.
one, just to get, maybe Western email will be better. Because so we'll then get in touch with you and details on how to come collect your prize. How do you do those clapping things? That's really cool. There you go.
There is
There you
a
go.
icon called reaction. Yes, yay!
Yeah. Okay,
Well, thank you.
Josiah, thank you
What's the
for
book about?
joining. Invite other people next time. Yeah. Anyways, I think that's it.
Okay.
And Khushi, you can wrap us up.
Yep. So thank you very much, everybody, for coming today. Thank you very much for this talk and also getting involved into discussion and helping us answer the doubts that we had while reading the paper. Thank you very much, Varun, for doing all that. And thank you very much for everybody for participating the quiz, which we have tried doing it for the very first time. So we really appreciate you doing that. And thank you so much. Is there anything I'm missing?
I have provided the answers to Khushi. So if you guys really want to know the answers, I think she have the answers.
Okay, so Khushi, you can stop the recording, then we can ask more questions if we only have a few minutes.
Yeah, sure.
Varun?
Sure.
Okay.
So what I'm going to propose is you can continue doing the discussion for next 7 minutes. I have another meeting to attend at 5. So we have 7 minutes. You can, and the stage is yours.